Thank you for watching Knowledge Academy.
Well, in single variable integral, we usually write like this. And we say this is integral over R, and R is my region, right? This is integral over R is my region. With iterative integral, we just write a little bit differently. We're writing two different ways. First we start writing like this A or R with dA. We start also writing with triple integral with V and dV. Sometimes we're writing D, sometimes we're writing D. Right? Here we have R, here we have a D. So line integral is nothing but it's just an integral over the line, not under the region. Right? It's going to be follow the line and finding certain quantity follows certain quantity. For example, line integral is very useful for calculation of work over a region, over a path or region. When I say region, is going to be just follow the curve. For example, if I'm asking you, there is a box, right? There is a box, I'm asking you this box, you want to move to box to point B, box is at point A. If it's going to follow the straight path, you can do it. But if it's follow the track, right? If you want a line integral, they can just basically use to calculate the work done needed to follow this track or this path. Okay. So another thing is that line integral it's a way to calculate to integrate over a scalar or vector function over a curve. It can be done in a 2D or 3D space, right? They have a many example, you can use this one to placing a satellite. You want to put a satellite in an orbit, you can use line integral. So you want to put the, let's suppose this Earth, you want to put the satellite supposed to be moving like this, and you want to put it over here so it can be start moving this way, dotted. So this spiral thing from the Earth, you lift and go this way, you follow actually a path to lifting up the satellite. It can be done like this. We can also calculate mass of a wire. Remember I give you a density function. So if somebody give you density function, you can take the line integral to finding the mass of the wires. You can also find the voltage generated in a wire or loop. I'm going to say loop, so wire is in the loop, so far so on. There is many application available. Okay, the line integral can be two different ways. The first one is called scalar field and then vector. I'm going to say scalar, the line integral of a scalar field or scalar function. The other one could be vector. The scalar function means you have like a 3D here. If you have a 3D and like this, and if I'm asking you making the line integral of this function, just you want to calculate some area, you basically making this yellow line, right? And this yellow line can be drawn in 2D. This is isometric view. If you want to look at the plane view, this yellow line is going to be look like this, right? And then you can just connect this to that. You can find area under the curve, like a typical in a vector field. If you have a vector field, and any vector field, let's suppose this is a vector field, and let's suppose this is a wind. This is a wind is blowing, and I'm asking you grab something. This is a street. This is a view of a street, and I'm asking you grab the stuff and cross the street. You can cross certain ways. You can maybe go here. So if I'm asking you calculate how much work you've done on this, you have to tell me about this. But this is called C. That is my path. Same thing. This yellow line is my path, or I can call curve. So line integral, line integral can also be called path integral. Okay. Now talk about a little bit let's talk about line integral of a scalar field and a vector field. So what I'm going to be doing, I'm going to be doing two examples side by side, scalar and vector. Okay. Here I'm going to be drawing a line. On the left side I have a scalar line integral. On the right side we have a vector line integral. Okay. And let's writing both evaluate. This C means curve and the integral means integral, and is giving 3x squared minus 2y ds, where C is the line segment from 3 6 to 1, and let's do 1 1, even 1 minus 1. Okay, I'm just writing a line here. I'm going to be saying evaluate. We're going to talk about how we're writing those line integral, and it's going to be C. Here I do not have a scalar function, I need a vector function. And vector function means I'm going to writing anything like f, but it has a little arrow on it, so it's a vector field. And I'm going to take again dot product with dr. We have a position vector here, so ds and dr have a difference. This guy 3x squared minus 2y and f have a difference, where C is a line segment from 3 7 and to 0 12, right? And I also did not give the vector field, like what is a vector function. and this is giving y squared comma 3x minus 6y. Okay, so a few differences we talk about that. That's a scalar of a path, that's a vector, that's a position vector, that is a function, and that is a 2 points are given, and that is a 2 points are given. So really you can find many things like str, you know. So what I'm going to be doing, I'm going to be just writing the line integral. So first I need to treat the c. What is c here and what is c here? Here I'm going to say c, I'm going to convert the c into parametric line. Parametric line, if you remember, x equals to x naught plus at, y equals to y naught plus bt, z equals to z naught plus ct. So here I'm going to say is for x component of this, I can write like this: x minus x naught, x equals to x naught plus at, right? Plus at, so what is my at? 1 minus 3 is going to be minus 2t. And then y naught is going to be 6 minus bt. Over there we say is x equals to x naught plus at, but here is going to be minus 1, and minus 6 is going to be minus 7t. That is my parametric equation. Over here, if I'm going to be writing, is going to be same thing. I want my line to be in parametric form, x and y coordinate, and I'm going to be writing here. I also need to write the value of t, so t is going from, the reason I'm just putting over here this one, if you substitute t equals to 0 here, like 0 here and 0 here, is going to be 3 comma 6 this point. If you're substituting 1 in place of t, so it's going to be 3 minus 2t is going to be 1, and 6 minus 7t is going to be minus 1. So if you substitute, bottom line is that if you substitute t value here, you should cut this. If you substitute this value of t, you should cut the other point. So t in between 2 point, 3, 6, 1 minus 1. So if you substitute value of t, you should get this point. If you substitute t value 1, you should get this point. This is how this limit is working. Anyway, I'm going to go to the other side and writing this so we can complete here. I'm going to say 3 x minus x naught, x equals to x naught plus at. So here is going to be 0 minus 3 is going to be minus 3t, and y naught is going to be 7, so not comma, it's going to be plus or minus, so 7, and then 12 minus 7 is going to be 5t. Again, value of t is going to go from 0 to 1. If I substitute 0, you should getting this point. If I substitute 1, you should getting this point. Okay, pretty much done. Here I'm going to be doing a little bit different. That's my solution here, by the way, and that is my solution. Now I'm going to be playing a little bit different rule on the left side and versus right side. Up to this point is pretty much similar. I want to parameterize my curve. dx over dt equals to minus 2, and dy over dt equals to minus 7. I just take the derivative of this and take the derivative of that. Okay, and I'm going to say this is my dx, this is my dx, this is my dy, so this is my ds, right? So ds equal to, my ds equals 2 minus 2 square plus minus 7 square dt. It's common coming out, and if I'm going to solve this, is going to be minus 53 dt. So ds equals to 50 square root 53 dt. So I'm going to write like this: c 3 x squared minus 2y dx. I can also write like this, 0 to 1, because that it has this dt, and then I'm going to substitute 3, and then I'm going to replace the x with, this is my x, this is my y, so I'm going to replace the x with 3 minus 2t minus 2, 6 minus 7t squared. This one is squared. Yeah. Now if we solve this and then I'm not done yet, I have to put 53, so I'm going to be removing this. It's going to be 53 t. If you solve this, you can solve this one. I mean, you open the parentheses and solve it, you're gonna get some answer. Solve this, gonna get some answer, and that is my line integral, right? This is my line integral for this particular function. On the other side, I have a f, my function f. I'm going to put the rt inside, right? And is equal to 7 plus 5t squared minus is going to be, yeah, all you have to do is just taking, this is my x, this is my y, right? I'm going to substitute into my function and then solve it. So 7 plus 5t squared, you're going to take 3 and then 3 minus 3t minus 6. So it's going to be 3t only. And 3 minus 3t minus 6, and then y value is 7 plus 5t. Okay, and then this is my function. So that's my function pretty much for f. And then r, I'm going to take the rt equals to, is basically I'm going to take this function and then take the derivative, which is going to be minus 3 comma 5. Right, that's my position vector. I take it, just same thing, I take the derivative with respect to, this is my r. Really I'm going to say is, this is my c, my c is my rt here. Okay, then what I'm going to do, I'm going to take the integral just like the other one and writing my function f r t dot r prime is my integral, and then t, and I'm going to convert this one. And from here, if I just substitute the value, it's going to be look like this, 3 7 plus 5t squared, then 5, and it's going to be 33, and this is, if you need to solve this thing, the whole thing, so maybe I can just write here, after solution is going to be look like this, 33 plus 90. Now this is pretty much another function we're going to be writing and then be solving, and we're gonna get the answer is, if this minus sign is coming, it means this field, either if it's a work or if it's a direction, maybe it's like a water is flowing, you are doing some work, so water coming out, water coming in, you are doing work, or work is done on you. So usually vector field came with the, or vector line integral came with the sign. Sometimes it's signed, sometimes it doesn't have a sign. Okay, so this is pretty much like a comparison for two. Now take a look on some line integral of little bit complicated, you know, functions. Let me just do it one more time. Okay. Now what I'm gonna do, I'm gonna go to next slide and do some problem for a little bit complicated line integral. This is C and that is my scalar field is given, or my scalar function. This is ds. Counterclockwise over a circle of radius 2, center at the origin. Okay, let's draw something. So this field is giving, look like it's a random field, you know, maybe it's like a pipe, you know, it's like a pipe. You cut the pipe into different location, and this is a pipe, and in the bottom is going to be turned to a radius of a circle. The radius of this is 2. We need to find this yellow vector, or sorry, yellow curve. We need to find the yellow curve, and then we go down like this way and then down like this way. Every location I'm going to be giving down, right, and then go to the other side, giving down on the back side. Basically, you can think about it, it's a pipe. It's a yellow color pipe. I cut it into a certain shape, and I want to know how big is the pipe, the area of the pipe. Okay, so I'm going to be writing my R, right? You can call this ds or directly call R, and then I'm going to be just using my parametric equation. So 2 my R cos t. If you remember, we writing the parametric equation in also in this form, x comma y. It can be written like this: R cos t, R sin t. So I can write like this. I can write this one equals to 2 cos t and 2 sin t. That is my x, that is my y. And what is my limit for time this time? T. So t always keep changing, so my t is gonna go from 0 to 2 pi, right? Now we should be very careful what kind of parentheses we are using. So this is a parenthesis we're using for time, just putting it inside the parentheses. So you know the time, if you put a t, it's not a time by the way, so it's a parameters. And if you just rotate it for 360 degree, you're gonna cover everything from all the value of x and y. Okay, if I take the r prime with respect to t equals to minus 2 sine t, then 2 cos t. Okay, I need to find the magnitude. So you can do this ds equals to dx squared plus dy squared, or you can find the unit vector through r. It's pretty much same thing. If I take the unit vector of r, is going to be doing this. Right, I'm going to be doing pretty much same thing, just a different way. Rather than calling ds this time, I'm going to call rt. And 4, 2 times 2, 4 sine square t plus 4 cos square t. equal to 4 1 sine square t plus cos square t equals to 1. So I'm going to get 1, and then this one is equals to 2. Okay, and I'm going to write this. So I'm going to say is area. This is the area equation looks like to me, the area of this pipe. I'm going to be writing this integral c. So right now I changed the ds to dt form. So I'm going to be writing somewhere dt right here. dt going from 0 to 2 pi. And I'm going to convert everything from inside this integral into my own parametric form. So it's going to be 2. Then x is 2 cos t square. Then plus 2 sine t square. And then close this. And then I want this guy with dt, because that's my RT. So 2. Remember earlier in the earlier example we use ds equals to something 53 dt. So this is my, this time this is my 2. Okay, I think it's pretty much a straightforward integral. Let's do this integral. I'm going to say is area equals to, I'm going to take the 2 outside, and this 2 I'm going to take it outside, and I'm going to say is 2 times 2 4 times 2 8 cos t cos square t plus 2 times 2 is 4 sine square t, and then dt. Maybe I can take common one more 2, so it's going to be 8 outside 0 to 2 pi, and then inside is 2 cos square t plus sine t, sorry, sine square t. All I did, I just take the 4 common and take it outside. Now here I can convert, before I take the integral, I can convert this to 8 2 pi. This one can be written in 1 plus cos square t. It's just a trigonometric identity, and I can just take the integral for this one. This one is equals to, I can also write this one 8 2 pi 0. 1 plus cos square t can also be written with this formula, 1 plus half cos 2t, and sorry, it's not going to be like this, there's more 1, half 1 plus cos 2t, and then dt. Now I think I can solve much simpler way, so let's do it now. I need to be fix this part a little bit before I take the integral. I'm going to take this, so it's going to be 2 and then 3 divided by 2 plus 1 over 2. I'm just simplifying, and then dt. All right, I'm going to take the integral now. 3 over 2 t plus 1 over 4 sine 2t, and then 2 pi 0 2 pi 0. Let's substitute the value and see what's going to happen. 8 3 over 2, and then 2 pi plus 1 over 4 sine 2 pi. then minus, if I substitute t equals to 0, this becomes 0 plus sine 0. Sine 2 is going to be 2 to 0, so it's going to be 0 everything. Okay. If I solve this one, it's going to be 3 times 2, 8, and 2 pi I think is also becomes 0. This guy also becomes 0. I'm going to take 8 times 3 is going to be 24 divided by 2, so this 2 cancels, so it's going to be 24 pi. That is my answer. Okay. Let's look at another example. I'm going to evaluate if C is a circle or C is a helix. Helix is just like this shape. Okay, C is a helix, R 3 cos t 3 sine t. Helix need 3 dimension, so I have a 3 dimension. That is my x, that is my y, that is my z. Okay, and it's also giving the limit. It's t's go from 0 to, like helix is basically 1, this 360 degree, then 720 degrees. So how many helix do you need? Like how many round do you need? So it's giving only one round. So it looks like something is just like starting the helix, gonna go there. Maybe just stop it here. This is 360 degree. Yeah. Anyway, we don't need helix. We know the formula of area equals to this. I can write here ds, or I says or I can write here like this. Make sure we just very clear about 2 ways of doing these problems. It's pretty much same thing, it's just a different way books are mentioning. I'm going to just rid of this and call, take the derivative, substitute the values, and then take the substitute the value and take the magnitude out. It's pretty much the same thing. We calculate ds. ds equals to dx squared plus dy squared. Here I just need to start solution. It's going to be relatively short problem, and writing t minus 3, and I'm just taking the derivative directly. So minus 3 sine t 3 cos t plus 1. Okay, if I want to do r prime t and I want to calculate the magnitude, double mod equals to, it's going to be 9 sine square t plus 9 cos square t plus 1. I can also write this 9, this whole thing taking a common, so it's going to be 1 plus 1 equals to 10. Okay, now I'm going to go to my integral and writing like 0 to 2 pi. Then I'm going to convert my function, which is y minus z. So y value is this, z value is this. That is my y and z. That is my y, that is my z. And I can just close this parenthesis and ds rate of y, this guy, with dt. I take this common, minus 3 cos t minus half t square, 2 pi and 0. and I'm going to substitute the value now. So 2 pi of sine is going to be 1, so it's going to be minus 3 minus, then I'm going to be put 2 pi cancelling, so it's going to be 2 times 2 is 4, so 4t square divided by 2 is going to be 2t, 2 pi square, not t square, 2 pi square, minus, I'm going to substitute the value of 0 here, so it's going to be minus 3, cos 0 is 1, it's going to be minus 3, minus, if I substitute 0, everything becomes 0. So answer is minus, if I take it, 2 10 pi square. That is my answer. Okay. Let's do one problem real quick for line integral over the vector field. So all I can do here, I'm going to just write in here 3 common way. Vector field or vector function line integral. The one I just told you, you can say is work done equals to line integral c force, or the function you can call force in terms of v, if you're talking about that, and usually write in dr, right? You can write in dr, you can, or you can write in like this, c for function dot d ds. These are unit vectors. You can write dr or uds. This u is a unit vector, that's why t is a unit vector. The third way you write in here, you can find a a shortcut. The shortcut is, to calculating this, you're going to write in, you split the function into 2 because it's a partial derivative. So I'm going to be writing the third one, I'm going to be writing, which is equals to c m dx and plus n dy. What is that? I'm going to talk about what is m, what is n, is nothing but basically is the component of function, x component of function and y component of function. Okay. So what is f? If you have a function is giving, you can parameterize this function into m and n. These are the 2 coordinates. And then dr equals to dx dy, right? If you want to be parameterize the position vector, you can just take the derivative. So really what's happened, you multiply the 2, so f dot dr means you're going to multiply this to this. So really you're going to be writing like this, m comma n dot dx comma dy. You're taking dot product of the 2, so you can write f dot dr equals to m dx plus n dy. And this is exactly what we did. This is how we come up with this. Yeah. Let's take a look at examples, how we can calculate this, evaluate the line integral of f over the curve f, and is giving like this. Okay. C, where my curve is C, is y equals to 2x squared from 0 0 to 2, 8. Okay, I know this formula. I'm going to write in here somewhere. W equals to m dx plus n dy. I'm going to be using this formula, and here I'm going to be writing my r function. So r equals to xy. I'm going to write in this parenthesis because this is a vector notation really, and I'm going to be also writing x equals to t. So x equals to t, so I'm going to say, x equals to t, y equals to 2x squared, so y equals to 2t squared. So I can write like this: t 2t squared. That is my x, that is my y. And t is going to be going from 0 to 2 this time. T is going to go from 0 to 2. How do I came up with these numbers always, right? That's a student have a common question, and I keep repeating. All you have to do, take the t value. Basically what you're doing, you're just substituting the value of t from, you're finding that value of t from this equation. So if you're substituting value of t, you're gonna get this point. So really you're gonna be writing something like this: 2t squared should be equals to 8. The value of t from here should be equals to 4, and then value of 2 should be equals to plus minus 2, so t equals to 2. That is how I get this. So every time you substitute the value of t equals to 2, you should be able to get 8. And every time you value substituting t equals to 0, you should be able to get in the other side, which is 2. And 2 and 8 are my coordinates of the points. Sorry, not 0, not 2, 0. So these are my 2 points. I'm able to substitute both. Okay. So I'm gonna get this one pretty much. Let's start it. My m, my n. My m equals to y, my n equals to x. So just to be clear, the y should be taking derivative with x dx. The x should be taking derivative with y. Okay. I'm going to be calling this y equals to 2t squared, x equals to t. So I can see this is my x equals to t, y equals to 2t squared. So if I take the derivative of dx, this one is equal to t dt, and if I take the derivative of dy over dt, it's going to be, all I did, I just take the derivative and take the dt from here and bring it on the other side. Same thing here, I take the dt here and then move on to the other side. Alrighty, I think I'm in a good shape to just substitute value inside my integral. Oops, no, it's not going to be t, it's not going to be t, it's just t, not a t squared, 4t. I'm going to be taking my integral and then substituting 0 to 2 is my limit. Then I'm going to take my function, so it's going to be 2t squared and y is going to be dt plus t 4t dt. Okay, all I did, I just substitute the value x dt, y dt. Okay, substitute the value. Now let's solve it. Before I do anything, I can say this is going to be t 4t squared plus 2t squared, so I can say 6t squared dt, then 2 0. Now I'm going to be take the integral. It's going to be 2, 6 over 3 is going to be 2, 6 divided by 3 is going to be 2, and then t cube, and the limit is 2 0. If I substitute 2, is going to be 2 times 2 4 8, and then 16 minus 0, 16 is my answer. Okay. Let's taking a 3D line integral in a vector field or vector function. Okay, field and function pretty much same thing. I'm going to be writing evaluate just so you know, in these problems, the function not actually telling you if it's a scalar or vector. Sometimes you have to decide it. Integral of f, you see, if I see this means a function is a vector. Or the curve f is given in certain form. Sometimes it's not given by words, it's just you have to take a look and then make a judgment. That is my vector field is given. And R is also given here, RT. Usually we creating one X, Y, so it's giving T square, T, and then TQ. T square, TQ. So really few things we're going to be writing about. So this is a question pretty much given. Before we start our solution, we know that W equals to C M dx, M is my y coordinate dx, plus N dy plus B dz. Okay, let's talk about what are those. So that is my N, that is my N, that is my B, that is my X, that is my Y, that is my Z. Usually we create our own by using parametric relationship, x equals to x naught plus at, or sometimes we use x equals to x naught plus at, y equals to y naught plus bt, z equals to z naught plus ct. This is for line. For curve, I'm just going to repeat these things because sometimes it's getting confusion, right? We usually say x equals to t and y equals to, whatever, 2x squared. So y equals to 2t squared. This is for curve. But you see, in the end, we're getting both in a t form. Here, we're going to get everything in t form. So here, the whole thing is doing for us. We already provided in a form that what we are looking for. Our job is much easier. Alrighty. So we're going to say is M and P, M and P. I already told you what is what. YZ, XZ, XY. So I'm going to substitute the value. It's going to be T4, T5, TQ. If I substitute these values, X and Y is going to be TQ. So everything is just like that. Then I'm going to take DX, DY, DZ. If I take DX, it's going to be 2T over DT. So T to 2T, I'm going to be moving here to bring it here. dy is going to be dt over, it's going to be just dt. And dz is going to be 2. So it's going to be 3t squared. And I'm going to take the dt on the other side and move it here. Okay, now I was going to write in this function, fairly simple, f dot rd, what it says f dot r c, or I can write like this, 0 to 2, and I'm going to substitute the value, this one, m dx plus n dy plus b dz. So let's substitute the values, going to be 0, 2, plus 3t 5 and then dt. If I do this, one is going to be t, everything is t5, so I can say is 2, 3 and 1 is 6t 5 dt is going to be 2 and 0. It's a fairly simple integral. We can substitute. It's going to be 6 over 6 t6 and 2 0. So it's going to be 2 to the power 6 is going to be 64 minus 0. 64 is my answer for this.
Thank you for watching Knowledge Academy. Please subscribe my channel.